First of all, welcome back to today's class, day number 9. In this course, MATH113, section 7, applications of mathematics in today's world. Now, in week number 5, we're still under the topic of applications of derivative, and actually, we need to talk about applications. All right? Applications of derivative. Do you remember what we have studied as of last week? This is a very important question. So if you want to know the answer, okay? If you want to know the answer, you need to go back to week number 4. Okay? You need to go back to week number 4. And one quick link that you need to make sure you visit at the end of each week is the end of week activity. Okay? In the end of week activity here, we have 2 specific sublinks. One is called process learning. The other is called content learning. Now, in the specific case of this course, I will strongly recommend you that you need to visit content learning every week, because there you have the suggested exercise, the completions of which will earn you the points along the way. And after that, remember, up to now, this is week number 5. I will strongly recommend you, if you need help to understand the specific background in mathematics, you come to visit Professor Leonard's videos, right? Okay? He's a very wonderful professor. Okay? We call him Superman professor. Okay? He has actually recorded his calculus class with detailed explanations of the steps. A couple of you asked me the steps earlier today. So if you need help, these are very good revisions for you to study at home. Well, for example, if you go to a specific tutorial house, if you pay per lecture, say $50 per lecture, you can count the number of $50 you need to pay for that. All right? So these are very important revisions. If you really need help, okay, without reading your textbook, or better say reference book, come to visit this. And the second thing you need to know is, up to now, because we are going through the MIT's open courseware, which is the specific course called, let me see, right here, yes, it's called, there is a specific number here. Yeah, okay, I will just ignore the number. We've gone through the first 3 important lectures ever since the last 2 weeks, okay? We start using this lecture in the second class of the second week. Actually, in the second class of the 3rd week, and this is the 5th week. And so we've gone through the first 3 lectures. Make sure you understand that at this point, you should have a good understanding of the definitions of the derivative of a functions. You need to understand the slope of a tangent line, which is one important geometric interpretations of the differential calculus. Example, use velocity. And then the rate of change is the physical interpretations of that particular differential calculus, or better say a derivative. And then we introduce limits, and we studied something about continuity. And then as of last week, we used the very famous trigonometric functions of sine theta over theta, and the limit as theta approaches 0. And what's the values of that? The trigonometric limit, and also the 1 minus cosine theta over theta, and the limit of this as theta approaches 0. And then we come back to a similar topic here in lecture number 3, with different ones understanding on this. And studying from lecture number 4 today, you will study the specific rule to do differentiations, the product rule, the quotient rule, the chain rule, and higher derivative. So before we start this week's lecture, this is something very important that I would like you to visit at the end of each week. This is called the recitation sections. The recitation sections mainly give you example problem solutions. And the way of doing this is very interesting. They will have tutor, okay, at MIT. Well, they will come into the tutorial class. The tutor will prepare a number of examples, and they will give the example problem to a class like this, and you practice the example problem using 5 to 10 minutes, and the tutor will demonstrate the solutions to you. Actually, we could try something like this, because as I could observe today, many of you are very much sensitive to the suggested questions, and you did find difficulty in completing them. So what I'm preparing to do is by Friday, I will try to pick some of the questions which is selected from the exercise, and I will distribute a different question to a different table. And you start solve the problems there on your table. And then we try to get each problem solved for you. And so each day will come here to share how you work this problem out. And that will be very useful. But one trade-off is, by doing that, you need to be disciplined enough to use the sources, particularly video. You need to watch them at home first. Now, I'm assuming that you did not watch those videos, so I'm repeating the videos here. And that is actually a tautology. That means I should have saved the time, not show you the video now, but start working on the problems. And then you can understand how much you learn from this, right? So if you promise that you watch the video at home, that means before you come to class, we can start doing that without wasting time. Eventually, in order to pass this course, you need to finish the suggested exercise at 20% or 100%. You need to write a midterm exam, which will give you another 20%. You need to complete a project, which will give you another 20%. The 60%, you can earn it like this in class, okay? And then finally, 40% will be the final exam, okay? So normally, students are so much used to the lecturing in class, so I start doing that by playing the video now. But actually, my preferred approach is you watch the related video at home, you learn them first, and when you come here, when we distribute an exercise for you to do, you practice what you learn, and then your question, you can solve it directly with you in class. So can we try something like this Friday? Okay? Because that is very important. If you just go home and do the exercise, you discover you don't know how to do it, you need to wait until you come back to ask me or use the hotlines to ask me. I can help, but so much better if you're willing to complete the video lecture at home and then we do the exercise here. How many set of exercise do you have to finish before you need to submit this coming Sunday and Monday? 3 sets. Remember that? 1 in week number 2, 1 in week number 3, and 1 in week number 4. So how many questions are there? I guess more than 20. Okay? More than 20. So you need to finish them. How many of you have started working on those problems? How many of you have finished working on those problems? All right. So let's try it on Friday. Okay? I'm going to deliver 3 sets of problems. We have 6 tables. So with 2 tables doing the similar sets. So 2 tables doing a week number 2, 2 tables doing a week number 3, 2 tables doing a week number 4. And then you can try it out. Okay? And then we can do it in class. That will be very meaningful. Because now it's starting week number 5. We really want to do something like this. Okay? Now let me show you a little bit about this. Suppose I give you a problem like this. Okay? These are problems. Okay? And then what are you going to do? These are basic questions that you learned over the past 3 lectures. Okay? So basically using the limit concept and using the difference equations. Alright? So these are coming from week number 4's end of week activity, particularly content learning. Please visit those links at the end of each week at least and study them, because exercise it here, examples are down there. Okay, all right. Work at solutions, and also the videos are already here. Okay, so it's very important you learn how to use them. For example, based on the definitions of derivative.
Hi, welcome back to recitation. In lecture, you've been computing derivatives of functions from the limit definition of derivative. So today, we're going to do another example of that and do some graphing as well. So I've got a problem written here on the board. So we're defining the function f of x to be 1 over the quantity 1 plus x squared.
Suppose you're supposed to do this.
What you do is graph the function, the curve y equals f of x, and to compute the derivative of f prime of x from the definition. So why don't you take a couple of minutes to do that yourself?
Can you try?
Then come back.
Take a piece of paper and try doing that. Can everybody try? Let the functions f of x is equal to 1 over 1 plus x squared. You need to graph the functions y, which is equal to f of x, and compute f prime of x. All right? Can you try doing this? Basically, you've learned how to do this in class already. All right? I'll give you 5 minutes. All right? Yes. You need to graph the functions, and you need to compute f prime of x. This is taken directly from last week's end of week activities. Okay, it's for a recitations example. Yes. Actually, it's 3 weeks already. It's given from the second week, from the third week, and also the fourth week, and it's due by the end of the 5th week. And on Friday, we will have different sets of questions that are taken directly from the suggested exercise. Let's see. Do you feel comfortable with this model of working out practices? Yes. Can you do that? Yes. You need to graph these functions, okay? Let's say we give you 10 minutes time to work this out, and then we see how it's being solved, all right? Have any idea how to work this out? Yes. How do you graph this function? going to do the attendance call, okay? So when the name is called, it's just raise your hand. Ricky, thank you. Alex, Johnson first, Johnson. Alex, and then Stella, thank you. Viviana, thank you. Jordan, thank you. Star, thank you. Chaos, thank you. You're new, thank you. Thank you. Louise, thank you. David is not here. Okay. Chen Chu, thank you. Viola, thank you. Candy, thank you. Mei Ling, thank you. Iris, thank you. Bella, thank you. Cindy, thank you. Vivian, thank you. Patrick, thank you. Jeanette, thank you. Ivy, thank you. Celia, thank you. Michelle, thank you. Lisa, thank you. Doris, thank you. Kelvin, thank you. Jeremy, thank you. Andy, Andy is not here yet. Okay. So 2 more minutes, and I'm going to invite some of you who've done the work to please come up to share your solutions. Okay? Any idea? Oh, you did okay. You have any idea? This problem. Seen it? Jeanette, you have any idea? Oh, you did something already. Okay, you want to share with us? In a minute. Okay, we got some workout. Got something. Thank you. Are you willing to share with us? Wow. Yes. Thank you. Okay. This looks very interesting. Yes. Okay, that's very good. May I ask for some volunteer? Let me set up the projector here. Okay. So any volunteer? Can you share with us your solutions? Would you like to do that? Let's see. Solutions. Do you want to share with us something? Your solutions? You want to? Okay, anyone would like to share with us your solutions? Anyone? You have the solutions? Okay. Over there? Anyone? Yes. Doris, can you come here? Thank you, Doris. You just put it here. Can focus. Let's see. Soup. Can you see that? Okay. Well, the best thing you want to see is my standard. That is here. What happened? We lost the connection. Yeah, that's one way we can do it. Let me give you a pen. Oh. Thank you, Doris. I hate to say that sometimes this machine does not work as expected. Yeah.
Is 0, the y gets 1. Draw this point. And when x gets 1, y gets half. Some points into the graph, we can draw the points and make it into a curve, and that is the curve. Y equals to and then let's find the derivative of y.
Just some technical problem. Thank you, Doris, for your patience.
It is obvious that the function is a composition function of two parts. So we can use the formula. First, we can find the derivative of this this one, and then find the derivative of this one, and then we multiply those two derivatives, and we can find the derivatives of y. My solution. Thank you.
Thank you, Doris. Thank you very much for your help. Now let's take a look at the particular part here, which is done by the MIT teacher. Wait, I need, in order to get back the sounds, I need to make sure that I will do something like this.
Try graphing this function in fx. So one thing you can always do when you start out graphing a function is to just plot a few points. And that'll give you a very rough sense of where the function is, at least around those points. So for example, when x is equal to 0, we have f of 0 is 1 over 1. So that's just 1. So we've got this point here, 0, 1. And when x is equal to 1, well, x squared is 1, so the denominator is 2, so the function value is 1/2. So, all right, I'm not going to draw this to scale. I'm going to put x equals 1 here, and the function value is 1/2. So this is the point 1, 1/2. And, oh, okay, we can do one more. When x is equal to 2, this function, 2 squared is 4, so that's 5, so it's a fifth. So I don't know, a fifth is smaller than a half, right? So that's maybe down here. So this is something like the point 2, 1 fifth. All right, but this is a very rough idea we're getting. So we can use some more sophisticated analysis to get a better idea of what this graph is going to look like. So the first thing we could notice, for example, is that this is an even function. Right? If I change the sign of x, if I replace x by minus x, well, x squared and minus x squared are both equal to x squared. So if you replace x by minus x, the function value doesn't change. So this is an even function that has symmetry across the axis here. So, you know, for example, I could just mirror image these points. So these points also have to be on the graph, the points -1, 1/2, and -2, 1/5. And any other part of the curve that I draw will be perfectly mirror image. Another thing to observe is that x squared is always greater than or equal to 0. So 1 plus x squared is always positive. So 1 over 1 plus x squared is also always positive. Also, 1 plus x squared, it reaches its minimum when x is equal to 0. And then as x gets large, either in the positive direction or in the negative direction, this gets larger and larger. This just the 1 plus x squared part. So if the denominator is getting larger and larger, while the numerator stays constant, the whole fraction gets smaller and smaller. So as x gets bigger, either bigger positive or bigger negative, the function value will diminish off to 0, and it has its maximum value here at 0, because that's when 1 plus x squared is its minimum. So the function sort of has its maximum here at 0, and then it flattens out. And as x gets larger and larger and larger, this goes to infinity, so the whole fraction goes down to 0. But it never reaches it, right? Because we said it's always positive. And similarly on the other side. Okay, so that's the graph of the curve y equals 1 over 1 plus x squared, roughly speaking. Okay, so now let's talk about computing the derivative.
Many of you did
So,
already.
right now, to compute a derivative, all you have is the limit definition of the derivative. So when I ask you to compute the derivative, what you've got to do is, write down what that definition says. So that's the limit of a difference quotient. So we have by definition, f prime of x is equal to, well, it's the limit, it's delta x goes to 0 of some difference quotient. So on the bottom of the difference quotient, we just have delta x, and on the top, we have f of x plus delta x minus f of x. Now, in our case, we have a nice formula for f of x. So this is equal to the limit as delta x goes to 0 of 1 over quantity 1 plus x plus delta x quantity squared. I guess I didn't need that parenthesis there. Minus 1 over 1 plus x squared. And the whole thing goes over delta x. So what would be really nice, of course, is if this were a limit where we could just plug in the value delta x equals 0 and evaluate it. But the way the definition of a derivative works, that never works, right? You're always left with the numerator as delta x goes to 0. That top is always going to be f of x minus f of x, and it's going to be 0. And the bottom is always going to be delta x going to 0, which is 0. So you always, when you have a differentiable function, you always have a derivative that's going to be a limit of a 0 over 0 form. So you need to do some sort of manipulation in order to get it into a form you can evaluate. So what we really like is to manipulate this numerator somehow and pull out, say, a factor of delta x. And then that can cancel with the delta x we have in the denominator. Some trick like that, some algebraic or other manipulation to make this into a form where we can plug in the value. So, all right, so right here, there's sort of only one manipulation that's natural to do, which is we can add these two fractions together. So let's do that, and we can rewrite this limit. The limit delta x goes to 0. So all right, I'm going to pull this 1 over delta x out front just to make everything look a little bit nicer. 1 over delta x times. Okay, so I want to subtract these two fractions. I want to put them over a common denominator. So the denominator is just going to be the product of the denominators. So that's 1 plus x plus delta x quantity squared times 1 plus x squared. Okay, so this fraction is 1 plus x squared over that denominator. And the second one is 1 plus x plus delta x squared.
You got that?
Okay, so we still haven't got where we want to be yet, because we still have this 1 over delta x hanging out. So okay, so we have to keep going. And so here, I guess this is a sort of a problem that forces us a little bit in one direction. There's not much we can do with the denominator, but here in the numerator we can expand this out and start combining stuff. So let's do that. So this is equal to, the limit hangs out. Limit of delta x goes to 0, 1 over delta x times, okay, so 1 plus x squared minus, all right, so if you expand out x plus delta x quantity squared, using your favorite either FOIL or the binomial theorem or whatever you like, however you like to multiply two binomials. So we get a minus 1 minus x squared minus 2x times delta x minus delta x squared. That's the top. Okay, we haven't changed the bottom. It's still 1 plus x plus delta x squared times 1 plus x squared. Okay, well, so what? Okay, so now some nice stuff is starting to happen, which is this 1 and this minus 1 are going to cancel, and this x squared and this minus x squared are going to cancel. And then after we cancel those terms, we see that in the numerator here, everything is going to have a factor of delta x, right? These 4 are going to cancel, and we'll just be left with these two terms, both of which are divisible by delta x. So that's where this cancellation we've been looking for is going to come from. So let's keep going. So we cancel those, they subtract, give us 0. So this limit is equal to the limit delta x goes to 0. Okay, and And then we can divide this delta x in the denominator in, and what we're left with upstairs is minus 2x minus delta x, the whole thing over the same denominator. 1 plus x plus delta x squared, 1 plus x.
So
All right, great. So we've done this manipulation. We finally found a delta x that we can cancel with that delta x we started with in the denominator. And now this limit is no longer this 0 over 0 form, right? When delta x goes to 0, the top goes to minus 2x. And the bottom, well, let's see, this delta x just goes to 0, so it's 1 plus x squared times 1 plus x. So that's not 0 over 0. We can just plug it into the value. So this is, just works out to a minus 2x over, okay, 1 plus x squared times 1 plus x squared is 1 plus x squared quantity squared. And so this is the derivative that we were looking for. This is, just remind you what that was, d over dx, 1 over y, 1 plus x squared. Now, if you wanted, you could check this a little bit by looking at the graph and looking at this function and just making sure that it makes sense. So, for example, this function, this derivative, has the property that it's 0 when x is 0, and that's the only time it's 0. And if we go back and look at the graph that we drew over here, we see that's also a property that this graph has, right? It has this horizontal tangent line there, and then it diminishes off to the right, and on the left side, so it increases, then it has that horizontal tangent line, and then it decreases. And so if we go back to this function, we see, yes, indeed, when x is negative, this whole thing is positive, and then at 0, it's 0, and then it's negative there. And similarly, you could note that this function here is an odd function. If you change the sign of x, that changes the sign of this whole expression. And so, okay, and so that makes perfect sense. Back here, the symmetry of this curve is such that, you know, if we look at a tangent line to the left of 0 and the symmetric tangent line to the right of 0, they're mirror images of each other. So their slopes are exactly the same. So that's a nice way you can sort of put the two different pieces of this problem together in order to double check. So that's that.
You see that it's a very good exercise for us to learn how to do exercise in this particular fashion. All right? So let me just make sure that I stop this. Okay? So this comes from the notes of last week, because towards the end of each week, we do have the end of week activity, and this is taken out from topic number 2. You can see the solutions through the video. And you can also try this problem with the solutions here to test yourself. But one thing I would like to comment on Doris, because she's actually going several steps further. She's applying those rules to help us to do differentiations. And those rules are supposed to be lecture of today. Okay? But in order to help one another here to pick up the skills, I think it's very worthwhile to do this, because the reasons I put this up here is because make it easy for you to revise. Okay? When you review something, then come here and try those exercises. Now let's try one more exercise, which is like what Star asked me. Do we need to graph the functions of the derivative? And normally we do, okay? And this is one way that we would like to show you this particular problem.
Welcome to recitation. Today in this video what we're going to do is look at how we can determine the graph of a derivative of a function from the graph of the function itself. So I've given a function here. We're calling it just y equals f of x. This is the curve y equals f of x. So we're thinking about a function f of x. I'm not giving you the equation for the function. I'm just giving you the graph. And what I'd like you to do, what I'd like us to do in this time, is to figure out what the curve y equals f prime of x will look like. So that's our objective. So what we'll do first is try and figure out the things that we know about f prime of x. So what I want to remind you is that when you think about a function's derivative, remember its derivative's output is measuring the slope of the tangent line. So that's what we're interested in finding, is understanding the slope of the tangent line of this curve at each x value. So it's always easiest when you're thinking about a derivative to find the places where the slope of the tangent line is 0, because those are the only places where you can hope to change the sign of the derivative. So what we'd like to do is first identify on this curve where the tangent line has slope equal to 0. And I think there are two places we can find it fairly easily. That would be at whatever this x value is. That slope there is 0. It's going to be a horizontal tangent line. And then whatever this x value is, the slope there is also 0, horizontal tangent line. But there's one third place where the slope of the tangent line is 0. That's kind of hidden right in here. And actually, I've drawn it. Maybe you think there are a few more, but we're going to assume that this function is always continuing down through this region. So there are 3 places where the tangent line is horizontal. I can even sort of draw them lightly through here. Just 3 horizontal tangent lines. So at those points, we know that the derivative's value is equal to 0. The output is equal to 0. And now, what we can determine is between those regions, where are the values of the derivative positive and negative? So what I'm going to do is below here, I'm just going to make a line, and we're going to sort of keep track of what the signs of the derivative are. So let me just draw, this will be sort of our sign on f prime. Okay, so that's going to tell us what our signs are. So right below, we'll keep track. So here, this, I'll just come straight down. Here we know the sign of f prime is equal to 0. Okay, we know it's equal to 0 there. We know it's also equal to 0 here. And we know it's also equal to 0 here. Okay, and now the question is, what is the sign of f prime in this region? So to the left of whatever that x value is. What is the sign of f prime in this region, and then to the right? So there really, we can divide up the x values as left of whatever that x value is, in between these 2 x values, in between these 2 x values, and to the right of this x value. That's really what we need to do to determine what the signs of f prime are. So again, what we want to do to understand f prime is we look at the slope of the tangent line as a curve y equals x. So let's pick a place in this region left of where it's 0, say right here, and let's look at the tangent line. The tangent line has what kind of slope? Well, it has a positive slope. And in fact, if you look along here, you see all of the slopes are positive. So f prime is bigger than 0 here. And now I'm just going to record that. I'm going to keep that in mind as a plus. The sign is positive there. Now, if I look right of where f prime equals 0, if I look for x values to the right, I see that as I move to the right, the tangent line is curving down. So let me do it with the chalk. You see the tangent line has a slope, negative slope. If I draw one that looks something like that. So the slope is negative there. So here I can record that the sign of f prime is a minus sign. Now if I look between these 2 x values, which I'm saying here is 0 and here it's 0 for the x values, and I take a point, we notice the sign is negative there also. So in fact, the sign of f prime changed at this 0 of f prime, but it stays the same around this 0 of f prime. So it's negative and then it goes negative again. It's negative then 0. And then if I look to the right of this x value, and take a point, I see that the slope of the tangent line is positive. And so the sign there is positive. So we have the derivative is positive, and then 0, and then negative, and then 0, and then negative, and then 0, and then positive. So there's a lot going on. But if I want to plot now y equals f prime of x, I have some sort of launching point by which to do that. So what I can do is I know that the derivative is 0. I'm going to draw the derivative in blue here. The derivative is 0. Its output is 0 at these places. So I'm going to put those points on. And then if I were just trying to get a rough idea of what happens, the derivative is positive left of this x value. So it's certainly coming down. It's coming down. Oops, let me make these a little darker. It's coming down because it's positive. It's coming down to 0. It has to stay above the x-axis, but it has to head towards 0. right? What does that actually correspond to? Well, look at what the slopes are doing. The slopes of these tangent lines, as I move in the x direction, the slope, let me just keep my hand, watch what my hand is doing. The slope is always positive, but it's becoming less and less vertical, right? It's headed towards horizontal. So the slope that was steeper over here is becoming less steep. The steepness is really the magnitude of the derivative. That's really measuring how far it is, the output is from 0. So as the derivative becomes less steep, the derivative's values have to be headed closer to 0. Now what happens when the derivative is equal to 0 here? Well, all of a sudden the slopes are becoming negative. So the outputs of the derivative are negative. It's going down. But then once it hits here again, notice what happens. The derivative is 0 again, and notice how I get there. The derivative is negative, and then it starts to, the slope of these tangent lines start to get shallower. Right? They were steep, and then somewhere they start to get shallower. So there's some place, sort of in the x values between here and here, where the derivative is as steep as it gets in this region, and then gets less steep. The steepest point is that point where you have the biggest magnitude in that region for f prime. So that's where it's going to be furthest from 0. So if I'm guessing, it looks like right around here, the tangent line is as steep as it ever gets in that region between these two zeros, and then it gets less steep. So I'd say right around there, we should say, okay, that's as low as it goes, and now it's going to come back up. Okay, so hopefully that makes sense. We'll get to see it again here. Between these two zeros, the same kind of thing happens. But notice, we have to be careful. We shouldn't go through 0 here, because the derivative's output, the sign is negative. Right? Notice, so the tangent line, it was negative, 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 0. Oh, it's still negative. So the outputs are still negative, and they're going to be negative all the way to this 0. And what we need to see again is the same kind of thing happened in this region, will happen in this region. The point being that, again, we're 0 here, we're 0 here. So somewhere in the middle, we start at 0, the tangent lines start to get steeper, then at some point they stop getting steeper, they start getting shallower. That place looks maybe right around here. That's the sort of steepest tangent line, then it gets less steep. So that's the place where the derivative's magnitude is going to be the biggest in this region. And actually, I've sort of drawn it. They look like they're about the same steepness of those two places. So I should probably put the outputs about the same down here. Their magnitudes are about the same. So this has to bounce off, come up here. I made that a little sharper than I meant to. Okay? So that's the place, that's the output. The output here, or the tangent line, sorry, the tangent line at this x value is the steepest that we get in this region. So the output at that x value is the lowest we get. And then when we're to the right of this 0 for the derivative, we start seeing the tangent line positive. We pointed that out already, and it gets more positive. So it starts at 0, it starts to get positive, and it gets more positive. So it's going to do something like that, roughly. So let me fill in the dotted line so we can see it clearly. Now this is not exact, but this is a fairly good drawing, I think we can say, of f prime of x, y equals f prime of x. And now I'm going to ask you a question. I'm going to write it on the board, and then I'm going to give you a moment to think about it. So let me write the question. It's find a function y equals, find a function g of x so that y equals g prime of x looks like y equals f prime of x. Okay, let me be clear about that, and then I'll give you a moment to think about it. So I want you to find a function g of x so that its derivative's graph, y equals g prime of x, looks exactly like the graph we've drawn in blue here, y equals f prime of x. Now, I don't want you to find something in terms of x squareds and x cubes. I don't want you to find an actual g of x equals something in terms of x. I want you to just try and find a relationship that it must have with f. So I'm going to give you a moment to think about it and work out your answer, and I'll be back to tell you.
If you think about it, Do you want to know the answer?
Okay, welcome back. So what we're looking for is a function g of x so that its derivative, when I graph it, y equals g prime of x, I get exactly the same curve as the blue one. And the point is that if you thought about it for a little bit, what you really need is a function that looks exactly like this function y equals f of x at all the x values in terms of its slopes, but those slopes can happen shifted up or down anywhere. So the point is that if I take the function y equals f of x and I add a constant to it, which shifts the whole graph up or down, the tangent lines are unaffected by that shift. And so I get exactly the same picture when I take the derivative of that graph, when I look at the tangent line slopes of that graph. So you could draw another picture and check it for yourself if you didn't feel convinced. Shift this curve up, and then look at what the tangent lines do on that curve. But then you'll see its derivative outputs are exactly the same. So we'll stop there.
Okay. May I ask you this question? Do you understand the meaning of shifting? When she talks about shifting of the graph, she's talking about shifting horizontally, left to right, or shifting ups and down. Which one do you prefer? Any idea? In order to preserve the slope, are we going to shift it ups and down, or shift it right or left? Okay, now this is a very interesting thing. All right, one more problem to go. Okay, let's go to limits and continuity. I would like you to keep the things that I suggest to you in mind. And let's talk about smoothing of piecewise functions. Okay?
Welcome back to recitation. Today we're going to talk about something you've been seeing in the lecture. Specifically, we're going to talk about continuity and differentiability. And we're going to use an example to see a little bit what the difference is, that how you can be continuous and not necessarily differentiable, and how it's a little stronger to have differentiability. So we're going to deal with a piecewise function. So I'm going to ask a question. I'll give you a little bit of time to work on it, and then we'll come back. So the question is the following. For what values of a and b is the following function either first continuous or second differentiable? So the function is defined in the following way. F of x is going to be equal to the function x squared plus 1 when x is bigger than 1. And it's going to be equal to a linear function where you get to pick the a, which is the slope, and you get to pick the b, which is the y-intercept, if x is less than or equal to 1. So what I've drawn so far, so that you can see, is that I've drawn the part of x squared plus 1 if x is bigger than 1. So I've taken the x squared function that starts at 0, 0, or the vertex is at 0, 0. I've shifted it up 1 unit, and then I've chopped off everything left of and including the value at x equal 1. So my question again is, what choices do I have for a and b to either first figure out what choices for a and b allow this function to be continuous when I put in the left part, so the values when x is less than or equal to 1, and what values for a and b allow this function to be differentiable. So I'm going to give you a moment to work on it yourself, then we'll come back and I'll work through them for you. Okay, so what we were doing again is we were trying to answer this question, choose values for a and b. First let's look at the continuity question. Okay, so what we really need is we need to have a linear function that ultimately goes through this point, whatever this point is. So we have to figure out what that point is, and then we can figure out what values of a and b will allow that to work. So if I want a continuous function, these a and b again, they have to be such that the line goes straight through that point. So what is that point? Well, the x value is 1. So what would the y value have to be in order to fill in that circle? We can actually look at f of x and we can say, well, if I wanted it to be continuous, then the y value I need at x equal 1 is going to be whatever the y value is here at x equal 1. So let me write that, make a little space over here. So to answer question 1, need A and B so that at x equal 1, y is equal to, well, if I put in 1 here, what do I get? I get 1 squared plus 1. So I get 2. So I need y to equal 2 when x is equal to 1. Okay? So in other words, down here, so again, let me just say, before I go on, this point is 1, 2. So what I need is a line that goes to the point 1, 2. Okay? So what is that? That would be, in this case, that would be, the output is 2, and the input is a times, well, x is 1 plus b. So that means a plus b has to equal 2. And that actually represents all the solutions. So there are an infinite number of solutions I could have. And if you think about it, I could draw some of these lines. So let's take, for instance, b equals 2 and a equals 0. When b is 2 and a is 0, it's the constant function f of x equals 2. It's a straight line. That would graph, I'm going to graph that here. That would graph straight across. I'm going to fill in right here. And this would be if we had on this side, this is f of x equals 2. Okay? I could also have chosen a plus b equals 2. I could also have chosen a equals 1 and b equals 1. So I could have slope 1 and intercept 1. Notice, by the way, this one is not differentiable, right? It's obviously there's a significant break there. We'll see also with a equal 1 and b equals 1, it's also not differentiable. So a equals 1 is slope 1 and b equals 1 is intercept is 1. That's this line. So this is kind of running out of room, but f of x equals x plus 1. Hopefully you can see that. F of x equals x plus 1. F of x equals 2. This one looks a little bit closer to being almost like the tangent lines are going to match up there. But it's not quite, and we'll see in a second what we will need. So this was, we answered the continuity question. Okay, so now let's answer the differentiability question. Okay, notice again, continuous, we have a lot of lines that will work. Okay. But to answer the differentiability question, I need the derivative as I come in from the left to be equal to the derivative as I come in from the right. So actually, I think I did that backwards. This is as I come in from the right, I need this derivative, gives me a certain value. As I come in from the left, I need a derivative coming this direction. I need them to be the same. That's what it would mean for the function to be differentiable. I can write that in words. The limit as x goes to 1 from the left, f prime of x, has to equal the limit as x goes to 1 from the right, f prime of x. I'm not sure, I think you saw this notation already. Limits coming in from the left are designated by a minus sign. Limits coming in from the right are designated by a plus sign. So we need these two limits to agree in order for the function to have a well-defined derivative at that point. So let's figure out what this is, because we have the function here. The function to the right of 1 is x squared plus 1. We know its derivative. Its derivative is 2x. So on this side, we have the limit as x goes to 1 from the right of 2x. And now we can fill that in. What is that? Well, I just evaluate at x equal 1, and I get 2. Okay? And now that means I need the limit as x goes to 1 from the left of the derivative to also be 2. So let's fill in this side. The function on the left, at the left of 1, is ax plus b. So what is its derivative? Its derivative is just a, right? Because the derivative of b is a constant, that derivative is 0. The derivative of this is a. Okay, so we get the limit as x goes to 1 from the left of a. That's what this left-hand expression is. Well, if I evaluate a at x equal 1, I can actually just plug it in. There's no x there. This is a constant function, so as x goes to 1 from the left, I just get a. So that tells me that a A has to equal 2 here. Okay? So in order to make the function differentiable, I only have one value of A I'm allowed to use. And that's when A equals 2. Okay? So I didn't draw this one yet. I didn't draw it on purpose because I wanted to save that for last. So when A is 2, what's B have to be? Well, in order to be differentiable, it first has to be continuous. So it has to satisfy this, A equals 2, and it has to satisfy this, A plus B equals 2. So that tells me A equals 2, that tells me B has to equal 0. That comes from our working number 1. Okay? What does that represent? That's a line with intercept 0 and slope 2. So I'll draw that one last. It goes through 0, has slope 2, so it goes through this point. And if I draw those, if I connect those up, we see, if we continue, we see that the tangent lines there agree exactly. But the function itself is just this part. It's the right-hand side is x squared plus 1, the left-hand side is y equals 2x. So we've now figured out how to make this piecewise function both continuous and differentiable. And we'll stop there.
Thank you very much. You see the review of the concept that we learned as of last week, the meaning of being continuous or functions to be continuous, and what are the conditions? And for functions to be differentiable, what are the conditions? Definitely, it has to be continuous. So you've seen 2 typical examples, actually 3. Now, and 2 more, now I recommend you, actually 3 more. Review this 3 more before you come back on Friday, and this will be very useful. On Friday, we'll finish the class by giving you exercise to do, at least for 30 minutes, and then we'll come back to the lecture. Okay? All right? So, oh, by the way, please help finish one important thing for this semester, because I was told. Please come to this website, click on this link. It's a 4-question survey for you to answer, because we need to keep that record based on the requirements of the department. So the 3 very simple questions on this survey, it's, do you believe the pace of this course is too fast, good, or too slow? All right? The second one is, how much do you understand about the course presentation? They provide this very interesting figure, and then I just would like your feedback, all right? Do you believe you understand 50% of the presentation or 100% of the presentation? And then how much do you understand about the course material, okay? And how much, all right? And finally, do you have any suggestions to improve teaching? These are very important midterm course survey. Would you please complete it before the end of the day so that we got the result and we can share with you on Friday, okay? Make sure you do it. If you don't do it, I'll ask you to do an exercise on this first, all right? So that's it for today on MATH113 section 7. And I hope you enjoyed today's practice, okay? And we will do practice like this in every class. At least I will reserve 30 minutes for this kind of practice to go through the lecture, all right? And I think it's very important that we think together, we do together. All right, I see you this coming Friday, all right?